Today you're going to study steady-state error in closed-loop systems. So what we've been doing so far was mostly modeling. And now it is time to close the loop and start looking at controlling a system that we modeled. The first step towards that is to evaluate now everything we evaluated before, such as transient, the steady state, but now when the system has a closed loop. And the system has a closed loop, the first thing we're going to look at is the steady state error. The Bode plot was the last element in the modeling analysis. And now we're going to shift the focus to controlling a system. And the first lecture on that is to evaluate the steady state error when you develop a controller. So by the end of this lecture, you should be able to understand the concept of steady state error, disturbance in a system, calculate the steady state error, and analyze the influence of control loop gains. So here's one example that we studied before when we were looking at a transient, but let's imagine that we want to develop a controller that will monitor or control the position of a laser system that operates on an eye. We want the system to reach exactly a specific point in space, and you don't want any error. How can you develop a controller that will make sure that the steady state error, once the laser has reached that position where the beam is supposed to go in the eye, it reaches exactly the point we want without any steady state error? Here's another application. This is more on mechanics. Let's assume that we have this rolling mill that is treating steel bars. So the steel bars are coming in and then they go through these rolls. The rolls are controlled to rotate at a given speed. But now when the steel bars get to it, they are changing the system, and potentially the speed of the rolls will decrease because of the added load and friction. How can you develop a controller to make sure that the speed never changes regardless of these external elements acting on the rolls? So to do that, we need to close the loop, and we briefly addressed that. And now we have these three elements in the control system. The process is what we've been studying so far, is how to model that. The controller is what controls the process, and we take measurements of that process to give to the controller. Now notice that again, the controller here takes the error between the desired and the actual position, the actual state of the system. And it takes action based not on the desired behavior, but on the error between the desired and the current behavior. So we need to make sure that this error ideally is always zero. It's always zero. The system always reaches the point we want. So let's look at a quick comparison once again between open and closed loop. The example of the roll bars that I gave, the mill that I gave earlier, was an interesting example to understand the effect of disturbance. The mill itself, or the rolls, would be the plant we modeled. Now there is something external to that system acting on it, and that is the disturbance acting on the system that is not part of the model, that cannot be modeled. So in an open loop controller, we can see that we have two inputs: the actual input that comes from the system, the controller, that we give to the plant, and there is a disturbance that acts on the system and affects the system directly. So R of S is our control input, T of S is external to the system, and we have no control over it. What we could do is to have a controller, but the controller doesn't get rid of disturbances, because you see in the second example here, we just added a control block to the plant. But now the output of the controller is also subjected to that level of disturbance that directly affects the output of the system Y of S. So the only way to get rid of that, or to mitigate the effects of any disturbance, is to close the loop. And by closing the loop, this is the new system we have here. We have the input. We take the input and compare with the desired output, with the current output. We calculate an error. The error, is given to the controller. The controller applies that to the plant, but the plant is subjected to the disturbance. But now notice here that the disturbance is taken into account indirectly through the feedback loop. We cannot get rid of it, but we can compensate for its effect on the output by including its effect on the error, because it generates an error, and this error is now taken into consideration when calculating the new control actions. So indirectly, we are compensating for the effects of disturbance, because the disturbance changes the error and the error changes the control action. We notice something else here that was added to the system, because you're now taking measurements. Measurements always, especially electrical measurements, will come in the form of, will add some noise to the system. So you're injecting some external noise to the control loop, and the noise comes from the sensor there. So now 3 inputs: the desired input, what we want the system to do, the noise that comes from the intrinsics of the sensors we are using, and the disturbance acting on the system. How do we calculate the final output of this system now? Well, there are 3 inputs, but we are dealing with linear time invariant systems. So the principle of superposition applies. If you just take one input at a time and calculate its output, we can then add everything, add all 3 inputs, and that will be the output of the system when all 3 inputs operate concurrently. And this only, again, works provided that the system is a linear time invariant system. So what can we further infer from this control scheme here? The main thing is that the control loop that we devise here has 2 main functions. One is to compensate for the effects of disturbance. The other one is to compensate for the effect of mismatch in the model. For example, if you got a parameter wrong, and if you got that parameter wrong in our model, it's not as critical as if we had an open loop system, because now the error will compensate for that. We can reject the effect of disturbance, improve noise attenuation that comes from the sensors, control the steady state error, and also control the transient response by calculating the function C of S properly. We can now make the system behave the way we want by choosing the function C of S and tuning it properly. So there are many ways to do that. Today, we're going to use the simplest one, and the simplest one is to set C of S to a constant gain K. What are we saying? We are saying that the control action that we are sending to the plant, it will be proportional to the error between the input and the output. And this proportionality constant is a gain that we have to define. So now let's analyze the effects of the disturbance in this system here. We have again 3 inputs. Let's do one at a time. So let's start with the disturbance itself. So this signal external to the system that cannot be modeled. If you want to evaluate data, then set all other inputs to 0. Rework now the block diagram to have T of S as the input. And for simplicity, you're going to neglect this and just assume that this is 1. So T of S becomes the input, Y of S is still the output, and you can calculate the transfer function of the system, the closed loop transfer function, by simply simplifying the blocks as we saw before. And this would be the equivalent transfer function of that system. G of S divided by 1 plus C times G. Again, G is the plant, C is the controller, T is the disturbance. Now we can repeat the process and look at the effects of the input itself, R of S. So set T to 0 and N to 0 and calculate the time response of the resulting system. Sorry, not the time response, the transfer function. And here would be the transfer function of that Y divided by R. And you can take this one step further and now evaluate the effects of noise in the output by simply setting R and T to 0. Rework the block diagram to find now the relation between N and Y. And this would be the response. So 3 inputs, evaluating one at a time. Because the system is linear time invariant, superposition applies, which means that the final output of the system is a linear combination of all other three inputs. So you can simply add everything up. And here is the final output of this system. You see that the output is not simply influenced by the input. That would be just the first element here. We also have two new elements now. One depends on the disturbance, one depends on the noise, and these two we have no control over. What you have control over is the function C of S, is the controller transfer function that you have to divide. That's the only thing we can control. T and N will always be there. So how then do we define that? Well, it depends. Depends on what we want to achieve. But let's assume, for example, that we want to reject the effect of disturbances and noise. That is, we don't want the disturbance and noise to affect the steady state error of the system. We want Y to go always to R, regardless of the value of T and N. So we can define the error, which is right here, as the input, desired input minus the current output. This is the error in the system, is simply the difference between the two. And we have an expression for Y of S, that's this big one we just calculated here. So you can replace that here, and we get the very first long equation. Input minus the output. We can rearrange the first two terms, just factor out S. Nothing else changes. Once we are there, we can find a common denominator for the first term and simplify the common denominator term in the numerator. And this is the final answer. This is the final steady state. Not the steady state, sorry. This is the error itself. The steady state would be the limit of that. This is the error in the system. We see that the error is also affected by three things: by the input itself, by the disturbance, by noise. We cannot simply ignore these. We have no control over them. They will always be there. But once again, we can control the controller transfer function. That is up to us to design. So let's see how to design that. I'm going to come back to this slide later. Let's skip to the next one here. So here is the error between the input and the output. So here we have the controller transfer function. Let me highlight that again. So if you remember from the last two lectures, these functions, they can be given in the frequency domain. And when they are given in the frequency domain, we can specify the cutoff frequency of these functions. We can let the system operate for a wide range of frequencies, ensure that the gain between the input and the output is large, so the effects of the input are transferred to the output. Or we can place the cutoff frequencies or the pole of a transfer function in a way that we only give it a very small range of frequencies. Say, for example, in a low-pass filter, we only allow certain frequencies to go through that will be reflected in the output, and past a given frequency, then the effect starts to be minimized because of the cutoff frequency of that specific transfer function. So one thing that we have control over is the magnitude of the transfer function controller, the controller's transfer function, at given frequencies, because that's up to us to design. Let's go back to the equation here. If we want to minimize the effect of disturbance and noise, should we make the controller transfer function magnitude large or small? It depends. Let's look at the second term. In the second term, we see that a C of S appears in the denominator, and we want the effect of disturbances to be minimized. So if you want the effect of disturbance to be minimized, then make the magnitude of C of S large, and that entire term decreases. But on the other hand, if you now look at the noise transfer function here, If you make the magnitude of C of S large, then you are amplifying the effects of noise. So that's the balance. How do we solve this? Well, now let's look at which frequencies these two will occur, the disturbance and the noise. Noise typically occurs at high frequencies. If you're dealing with electronics, it will be something that will occur at a much higher frequency than the disturbance itself. Considering the mill that we had as an example in the beginning, let's say we are measuring the speed using a sensor. We are injecting noise into the system, and this noise could be in the order of kilohertz in frequency range. We have one steel bar coming at a second, for example, through the rolls, which means that the disturbance itself will only occur at 1 hertz. So we can say that this is actually an example that works for most systems. We can say that disturbances occur at a much lower frequency than the noise, which means that now, as designers, we can simply make the controller transfer function large at low frequencies, because at low frequencies, this will then tend to 0, and make it high at a high frequencies, which is where this term here occurs. And then that term is also minimized. So the solution is just to play with their cutoff frequencies. Remember the Bode plot, and make C of S large at low frequencies. So this term that occurs at low frequencies decreases, and make C of S large, small at a high frequency. So this term here that occur at a high frequencies is also minimized. And we still have, of course, the transfer function between the input and output, and that one then reflects the input directly to the output. Okay, so as designers, then we need to find an appropriate function C of S that works for our system. As I said, today what we're going to look at is simply to set C of S to K. It's just a constant gain, and this works for all frequencies. So this is not necessarily addressing any of these concerns here, but it's a first approach to see how the controller affects the behavior of the system. Are there any questions before we move forward? No? Okay, so this picture is familiar to you. Now I have still two phases, the transient and the steady state. And now we have our feedback loop, and we want to evaluate how the feedback loop is affecting the steady state value. And then later we'll go back now to transient and see how that affects the transient. So going back to our original system with 3 inputs, let's consider noise and disturbance to be 0. And if that is the case, we are only left with the input R of S, and the steady state error, as we calculated before, would just be the first term of that big equation. The steady state error, we can now calculate, sorry, this is the error, not the steady state error. The steady state error is the limit of that error when time tends to infinity, or the limit of the error times S, don't forget the S from the theorem here, when S tends to 0. If we now evaluate the system for a DC input such as a step input, then the input R of S becomes 1 over S, and we are left with this. And when we make S tend to 0, all transients are gone. We are left with the steady state value only. So C times G is what we call here the DC gain. As well, we ignore the effect of all transients in the system. Right? So there is a steady state error, and you notice that the steady state error depends on the magnitude of the controller transfer function when S tends to 0. Now let's give a practical example here. So here we have a function g of s that we want to control. And we are developing a controller for that function. The controller is c of s. The steady state error in this example is simply the difference between the output and the input. Input is r, output is y. So the steady state error is simply r minus y. Right? And what is y of s? Well, y of s we can calculate easily. Is just k over tau s plus 1 times ka tau 1s plus 1. Taus are constants. All these times r of s. We can now replace this in the equation for y of s, and you're left with the big equation in the center. E of s equals to r of s minus the transfer function itself. And now let's calculate the steady state error for a step input. So the steady state error would be the limit when s tends to 0 of s times the error itself, which is the limit when s tends to 0 of s times r of s for an input, step input is 1 over s, minus kka tau s plus 1 tau 1s plus 1 times r of s, 1 over s. So these ones will cancel out. And what is the final value here for this, the error when s tends to 0? What is the result of this limit?
It is 1 minus kka.
1 minus kka, very good. 1 minus kka. Now let's look at this result. Ka comes from the plant, comes from the process we are trying to control. We can't change it. Ka is what it is. K, however, comes from the controller. So K is up to us to design. How can you make the steady state error 0? By choosing K to be 1 over Ka. This is the only way to make the steady state error 0. This implies that we need to know exactly how the plant behaves. We need to have a perfect model of the plant and the perfect estimate of Ka so that we can tune K as the inverse of that. So this is not always the case, but sometimes it is impossible to fully capture the dynamics of a system. This approach, therefore, only works for an ideal model where you have perfect knowledge of all elements in that model. And there's only one way to make the steady state error, is to set the controller gain to 1 over Ka. Right? Provided again that we know Ka, we must know Ka. Now let's do the same, but let's use a closed loop controller instead. And if you do a closed loop controller, you guys remember how to find the transfer function of this closed loop system. Let's assume that this entire thing here is called h of s. What is the transfer function y of s times r of s? Is h of s divided by 1 plus h of s. You remember this from a few lectures ago? Yeah?
Yes.
Very good. So now we can find the transfer function. H of s is just the multiplication of this times that. Find the transfer function and do the same. So this here we have now the error, the input minus the output, and the output is simply y of s, which is this entire function that we got from that. And you can now do the same, calculate the steady state error. Let's do that. The steady state error is the limit when s tends to 0 of s times e of s, which is the limit when s tends to 0 of s times, for a step input, r of s is 1 over s, minus kka tau s plus 1, tau 1s plus 1, plus kka. So this is the difference now compared to what you had before, because now it's a closed loop, the transfer function has changed, and kka made it to the bottom too. Times 1 over s for r of s. So this s will cancel. And what is the result here? Is the limit when s tends to 0 is what? Your steady state is 1 minus kka divided by 1 plus kka. We can find a common denominator here. 1 plus kka. That gives 1 plus kka minus kka, which is 1 over 1 plus k times k. Terrible hand writing here. 1 plus k. That's the steady state error. Now let's look at it again. Here is Ka, the plant, the gain that we cannot control, and here's the one we can control. How do we make the steady state error 0? There is no way to make the steady state error 0. We can minimize the steady state error by making K as large as we can, as large as the plant accepts, as large as the drivers accept before reaching saturation. But we cannot fully eliminate the steady state error. But we can minimize it. You may say, well, the other one was better. Well, not really, because this one you must know exactly what 1 over Ka is. And what if during operation Ka changes? Then your controller doesn't work anymore. Whereas this one, it's a lot easier to implement. Just set the controller gain K to a high value, and that will minimize the steady state error even when Ka changes is likely. Right. So two approaches. First one, only one way to minimize the steady state error in the open loop, in the closed loop. Now, the steady state error is never 0 for this particular case, but it may be minimized by manipulating K, by setting K to a high value. Okay, so that's the trade-off. Are there any questions?
Could you just go back to the open loop slide for a second, please?
Yep.
Okay, that's great. Thank you.
Any questions? No? All right, so let's do some examples that will help clarify this new concept. So you have in this first example here is a system that was developed in 1987. That's quite early, to regulate the arterial pressure in intensive care unit patients by infusing sodium, sodium something. The body reactions transfer function is given by data transfer function. And the controller is a proportional gain, so that the controller equals to K. Calculate the steady state error for a step command A as a function of K, which means that we want to infuse a amount A of insulin in the of sodium in the body. We want to calculate the value of K that I will as a function of calculate the steady state error as a function of that controller K. So this was developed in 1987, so probably works with a some sort of analog controller inside there using operational amplifiers, or maybe even some sort of small, simple digital controller. But early control systems methods, they used analog operational amplifiers to implement the control scheme. So there you have the plant itself, which is the body given by the function g of s. That is how the body reacts to that, that drug. And we have a controller k. So the first step here is to now develop the control scheme for this. We have two parts: the controller, the plant, and the gain. So here, sorry, and the feedback loop. So here's the feedback loop. We have 1 over s plus 10 squared. This is the plant, this is the body. And we have the controller k that now takes the error between the desired input r and the current input y, multiplies that by a certain value, and we give that to the plant as the control command. We are giving this system a step input of magnitude a, so r of s is equal to a over s. We are interested in the steady state error. Sorry, the steady state error is over here. The error is there as a function of that controller k that we have to calculate. Is this control scheme fine? Any questions about that? How that came to be? Yeah, here it is. Have more questions about it? Let me know. Okay, you can see. So you want to calculate now the steady state error based on the value of k. So once again, here is the body reacting to the injection of a drug, reacts with this is the variable we are measuring, whatever that is. Send that to the controller, and then the controller multiplies the error by a constant. So notice that when the y and r are the same, this is 0, nothing is given to the body. And when it's not 0, then we keep injecting something until we reach that specific point. So let's calculate the first step. Here's to calculate y of s. What is the equation for y of s over r of s? That's the closed loop transfer function.
Hs over 1 plus Hs?
Right. H of s, which is this 2 multiplied, k over s plus 10 squared, divided by 1 plus that. And this simplifies to find a common denominator here. The common denominator is s plus 10 squared. So we can extend this, and if you extend that, multiply 1 here by s plus 10 squared. Will give us that. Now this and that simplify, and you're left with k over s plus 10 squared plus k. Okay. So this is y over r. If you move r to the other side, we have an expression for y of s. Just multiply this by r of s. Are we good with the closed loop transfer function?
Yeah.
Yeah. Very well. What is the error? The error is the desired input, which is r of s, minus the current output, which is y of s. Y of s is this. So we can now recalculate the error as r of s minus all that, k s plus 10 squared plus k times r of s. The error is r of s times 1 minus k s plus 10 squared plus k. Okay, we are applying this system according to the question. a step command of magnitude A, which means that R of S is A over S. It's a step command of magnitude A. We are injecting A units of sodium in the body, or we want to. Okay, so now we can take this expression and evaluate that in steady state. So the error in steady state is the limit when S tends to 0 of S, don't forget the S from the theorem, times E of S. Is the limit when S tends to 0 of S times, what is E of S? This is entire expression here, and now we can replace R with A over S times 1 minus K over S plus 10 squared plus K. So this S and this S cancel, and we are left with error in steady state, which is, what is the result there? A times 1 minus K divided by 110 squared plus K. We can further simplify this. Let's find a common denominator here is 100 plus K. That's 100 plus K minus K. So the error in a steady state is 100 times A divided by 100 plus K. What can we tell from this expression? We can say two things. The first one is the higher the step, the higher the steady state error. The higher the gain K, the smaller the steady state error. So we can control K, make it as large as we want to develop a steady state, to minimize the steady state error for this step command. Now, why don't you just make K infinity? That would fix the problem. Why can't you make K tend to infinity? Well, problem is that K is the proportionality constant here that it gives the amount of drug we are injecting in the body compared to the error between the input and output. So if K is too large, then a very small deviation here would inject an enormous amount of drug in the body. That wouldn't work. That would not work for practical reasons and for safety reasons. Of course, we don't want that to be injected into the patient's body, but also there is a limit of how much we can physically make the system inject. Right? So there is, what limits this is mostly the hardware that composes the device itself. Are there any questions here? Any questions? No? Okay, well, if there are no questions, this is all clear. Let's do exercise number 2. Here it is. I'll give you guys 2 minutes as I raise the light board to try this. Just
Sir,
create.
Could I quickly see the board again?
Yep. So start looking at exercise 2. 2 things as I raise light board: create the block diagram and also try to find the closed loop transfer function.
Okay.
So this example is a bit different. We have a mechanical ventilator, and the objective here is to achieve adequate gas exchange while minimizing lung injury. So we need to be very careful with the transient and the steady state value of the airflow and air pressure, both the quantity of air and the pressure at any instant in time. The rate flow in this case can be characterized by a ramp function that goes up and down. And the transfer function of the ventilator flow rate as a function of the voltage input we give to it is given by H of S. If a proportional controller is used to regulate the flow, calculate K that it yields a steady state error of 0.1 liters of air for a ramp input of 10 liters per minute. All right, so let's do that. So what is the closed loop transfer function for this one? Has anybody got to that?
Did you ask for the transfer function, sorry?
Yes, what is the closed loop transfer function? Y
Y of S over R at S equals 100K over 0.001 S squared, or yeah, that.
Yeah.
Yeah,
Yeah, times R of S.
R at S, yeah.
Okay. Yeah, so I'm just using tau here for tau is 0.001 just to avoid writing that over and over. Because the steady state value is never affected by the time response, right? So, by the time constant, excuse me. By the time constant. So this is why, anybody has questions about this function?
Oh, shouldn't you also have 100K on the plus 100K on the bottom? Yeah.
Yes. Anybody has questions about this function? So it's this divided by 1 plus this. And we get there. So if we hear nothing, I'm going to continue. Okay? All right. So what is this, the error? What is the error? The error is always the input minus the output. Here is the output of our system. So the error is R of S minus 100 times K S tau plus 1 plus 100K times R of S. We can factor out R of S as we did before. 1 minus 100K S tau plus 1 plus 100K. We want to evaluate the steady state error when, we want to find the value of K that it gives a steady state error. So a steady state error of 0.1 liters. What is the value of K? When the input is to the system is 10 liters per minute, is a ramp of 10 liters per minute. What is the function R of S?
10 over S squared.
Exactly, 10 over S squared. Okay, now we have pretty much everything. We can calculate the limit when S tends to 0 of S times E of S, which is the limit when S tends to 0 of S times R of S, 10 over S squared. 1 minus 100K divided by S times S tau plus 1 plus 100K. What is the result here? This S cancels one of those s's. So if you make s tend to 0, this tends to infinity, there's something wrong with this. Well, not really. We can first manipulate this part of the equation here, see what we get there. So we have now the error in steady state is the limit. When s tends to 0, I'm going to do the simplification here. This s cancels that one. Remember, there's still one left. And inside here, we can find a common denominator. The common denominator is ss tau plus 1 plus 100k. So this multiplies 1. Minus 100k. Aha. Now these two cancel out. You see? Those two cancel out. And this s cancels that one. So the mystery solved. What is the result now when s tends to 0? 10 times up here, this all cancel out. We have 1 divided by, this is all 0, 100k. What do we do next? That's the steady state error for as a function of k. The question states, find a appropriate gain k that yields a steady state error of 0.1 for this particular input. So we can simply equate this to the desired steady state error of 0.1. Which means that a k is, what's the value of k?
1.
1. When k equals to 1, we get a steady state error of 0.1 liters when the input is a step command of 10 liters per minute, 10 over s squared. Sorry, ramp, not step. Questions?
Yeah, how do we know it's a 10 over s squared for the RS?
Where did this come from?
Yeah, was it because last problem was just s?
Yeah, so the last problem, the input was a step input. In this problem, the input is a ramp input of 10 liters per minute. So the blood flow, the airflow that we want is something over time. So this would be R of t is something like that. 10 liters per minute. So in 1 minute, it would go up to 10. All right, so this in time domain is 10 times t. In the frequency domain is 10 over s squared. In the previous example, the steady state error was calculated for step command A. So in the previous example, we just have a constant step command of magnitude A. This in time domain is A times u of t, and in frequency domain is A over s. All right, step ramp. Is it clear?
Yeah, it makes sense.
Okay. Any other questions? Are there any other questions? No, this is relatively simple. Just don't forget to, especially when you deal with the ramp inputs, to do this small operation inside here. Sometimes it will cancel out, but it is only canceled out because of this S, right? So if this S wasn't here, the steady state error would tend to infinity. All right, so if there are no questions, let's do one more. Yeah?
Sure.
Let's do exercise 3. I'll let you guys read it as I erase the whiteboard, and then I'm gonna get to it. See, in the previous example, if K was not the right one, if you selected the wrong K, then we would be delivering probably not enough air through the ventilator because the steady state error would be too big. But this one is a bit different. This is a model of the body, and it represents how the body handles glucose levels. There's a lot of studies showing that there is a negative feedback loop, and the body takes actions to maintain a certain glucose level. And if it takes action based on an estimation and a measurement of glucose level, it has an inherent feedback loop somewhere through its physiological mechanism. And let's assume that that is represented by a block diagram such as this one. When the blood glucose level is too high, the pancreas secretes insulin, and when it's too low, it secretes something else. So there is clearly here a feedback loop to measure how the blood glucose is, and then take actions based on that measurement. Let's assume that such a mechanism can be represented by this block diagram and determine the steady state error for a unit ramp disturbance. So what are we looking at? So we have a system. Let me just put it here. We have this block diagram that represents the body, how the body reacts to insulin and how it controls its glucose level, not insulin, and how it controls it. Two inputs. One is the input the body wants to maintain at the level at, that's R of S, that's the desired level that the body, target level for the body. That's the actual level that the body is somehow doing a feedback loop. And T of S is a disturbance. This disturbance could be anything that is outside of this self-regulating mechanism that is affecting how the mechanism works. I don't know, it could be blood pressure, it could be ingesting more glucose by eating something, or it could be an injection, it could be anything else that is not part of the self-regulating system, is external to it, and therefore the self-regulating system can only take that into consideration by looking at the effects that it causes in the air. But it cannot estimate, or can it get rid of that input completely. We want here to calculate the steady state error for a unit ramp disturbance. Unit ramp disturbance. These are parameters of the system itself, an integrator here that symbolizes the plant. And you want to evaluate the steady state error to a unit disturbance. So if the disturbance is what we are trying to evaluate, then we need to set everything else, all other inputs, to 0, and then find the appropriate transfer function between the disturbance and the output. We can set now this to 0 and see how the disturbance affects the output directly. So let's do that. When that input goes to 0, the new input is T of S. So let's now rearrange this block diagram to have T of S as the main input to the system. T of S here goes down to this sum in a negative sign here. Then it goes through the integrator, and the output here is Y of S. then what happens? Then you have two feedback loops. One that is multiplied by K2. The other one that is multiplied by K. Notice now that we are putting them both into a sum. They go into the same sum, so this could just go there directly, it would be the same. So we can add these two to the same sum here. It's a negative sum, negative and negative. Right? But then we are multiplying that signal by K1. And then adding this over there. I notice that these two negative signs, I can put those two negative signs here. Doesn't change anything. Or I can put two negative signs here and a positive there. Works as well. I'm just moving two here. Are we okay with this? Are there any questions about this equivalent block diagram? We can further simplify it actually. So T of S goes to that negative sum, then 1 over S, then y of S. Now notice what is happening down here. We are adding K1 and K2, so we could put them together, K1 plus K2. And you're then multiplying that by K1. Sorry, this is K. Yeah, this is K and this is K1. And then we are moving that up to the sum. Are there any questions here? Is this simplification okay from this to that?
Yep.
Yeah, and this to this, fine too.
What about RS?
R of S, we set that to 0.
Why?
Because you're evaluating the effect of the disturbance in the outputs. You can only evaluate one at a time based on superposition as we saw before. So if you want to do T to Y, we have to set all other inputs to 0.
Thank you.
Okay. So if this is fine, now let's find the transfer function T of S over R of S. And what is that transfer function? Let's do a generic one here. So we have now two functions. We have everything we did so far. I think we only saw ones with the unit feedback here. Let's call this function H. And let's call this function in the feedback loop here G. So that's R. I'm going to omit all S's for simplicity. What is the equation for Y? Y is this signal times H. So H times this signal here, which is R minus Y times G. R minus Y times G. Here is the signal times H gives Y. Okay, so we can multiply this out. Y plus H Y G equals to HR Y1 plus GH equals to HR. And now we have Y over R as H divided by 1 plus HG. All right, so the only difference compared to what we saw before is that this was 1 before, but now it's a function G of S. What is h in our case? H is 1 over s. And what is g? G is k1 times k plus k2. Are we good? Any questions here?
Professor, could you please explain why H, what is H and G? And here, is that means if we find out the relation between the R and Y, we just consider T as B0, or it is included in the system?
These are all functions of s.
Okay, then, so here TS has been included, right?
No, this has nothing to do with this yet. This is just a generic way to find the transfer function from a block that resembles this one, which is that, right?
Oh, okay,
Now,
got it.
In our example, h of s is 1 over s, and g is this.
Yeah.
Right? I'm just wanted to derive that equation.
Okay.
Professor, do you mind
Yeah.
going over the derivation again?
Yeah, so which part?
So you said y, like how'd you get y again?
Yeah, okay. So this signal here is signal R minus this signal. Let's call signal B. So this is R minus B, correct?
Yeah.
And what is B? B is Y times G.
Mm-hmm.
Y times G. If this signal here is R minus Y times G, Y is this signal times H. Y is that signal times H.
Okay.
I take this, multiply by H, you get that. Okay, and now we just need to work out the math here to isolate, find exactly Y over R.
Thank you.
Okay, so let me erase this. Now we have the generic expression for this feedback loop.
So Professor, in this case here, the R actually equals to TS, right? Because we built that model for this one.
R equals to TS, yes.
Oh, yeah.
Okay. So we have here basically the line function, top function, 1 over s, divided by 1 plus the line function itself, 1 over s, times the feedback function, k1 times k plus k2. And that's t over y. How can you solve this? Well, we can find.
Is that y of s and not r of s?
Yes, that's y of s, sorry. Thank you.
Professor, I have a question here. So here in this model, because the TS is negative to the system, so usually we consider it as a positive.
No, we are going to change the add negative to that as well, one step at a time.
Okay.
So, all right, so let's do again. So this is indeed y over y, TS over y. And because of this negative sign here, which would be equivalent to having a positive sign and a negative 1 multiplying there, you can just multiply the whole thing by negative 1. It's not very visible. Let me make it more clear. All right, this negative sign makes its way here. How do we solve this? T of s over y of s. We find a common denominator. Common denominator is s plus k1. Not enough space. So 1 over S plus K1, K plus K2, all over S. That's T over Y. Now this S cancels that, and we are left with 1 over S plus K1 times K plus K2.
Professor, what about the negative side?
Professor, why is it T of S over Y of S?
Why?
Yeah, isn't it
Well,
output over input?
this transfer function, right? It's this is the input, this is the output. Is did they flip it? Yeah, I flipped it. It's Y over T, sorry.
Oh, okay, thank you.
Yeah. Sorry about that. Right? Output always divided by input. Right? Output is Y, input is T. Sorry about that. Good catch. Okay, that's the final expression now. And we now want to calculate the steady state error. To calculate the steady state error, we need the output. To find the output, just multiply both sides of this equation by T. So Y of S, the output is negative 1 over S plus K1, K plus K2 times T of S, which is our input. What is the error? What is the error?
Would it be T at S minus K1 bracket K plus K2 times Y at S?
Correct. So that's where the trick is. Is the error T of S minus Y of S, or is the error 0 minus Y of S? What is our desired input to the system?
R of S.
Is R of S, which is 0.
So it should be the second one.
It should be the second one. Why is not the first one? Because the first one we would be comparing how the disturbance, the error between the disturbance and the output. But that's not the error we evaluate in the system. The system error is defined as the input and the output relation. Right? By setting this to 0, we say that anything that deviates from 0 in the output comes from the disturbance, and therefore that's the effect of the disturbance on the on the output. Right? It's not how far the output is from the disturbance. That doesn't matter. It's how far the output is from the input, and the input turns out to be 0. Anything that shows up in the output now is not because of our input, it's because of the disturbance. So this highlights the effect of the disturbance directly in the output. So it has to be 0 instead of T of S. Right? The first one doesn't really help us analyze the system. So this is in fact R of S minus Y of S. That doesn't change. This is 0. Does it make sense? So the error now becomes 0 minus that. So now plus 1 over S plus K plus K2. And let's make this a step input 1 over S. That's the error at all times. The error in a steady state is the limit when S tends to 0 of S times E of S. And
I
what
just
is
have
the
a quick question. Why is T at S equal to 1 over S?
we are assuming a step disturbance. To determine the steady state error for our unit ramp disturbance, in the question. Let's do a step.
So like we should erase ramp disturbance and put
Yeah, let's
step.
do a step.
Okay.
You understand why soon. So let's do a step.
So if there is a ramp, then it's 1 over s squared, right?
Correct.
Okay.
So what is the steady state error? Is the limit of s times all that?
So it would be 1 over k multiplied by k plus k2.
Correct. So this is 1 over k, k1, sorry, k plus k2. What's the steady state error to a unit step disturbance? If we had a ramp, what would have been the error? This would become 1 over s squared.
Would it be 0?
It would be infinity.
Yeah, it would be infinity because there is a s when in the bottom it should be 1 over 0.
Right. So this is a step. If we had a ramp, this would have been squared, and then would have the limit of 1 over s. When s tends to 0, it would tend to infinity. And that would make perfect sense. This is what we are saying here. If the system is subjected to a step disturbance, then the output in steady state, so it will have some transient, and in steady state will reach something like that, and this value is 1 over k, k plus k, whatever that is. All right, this is time, and this would be the result to a unit step disturbance. So something applies here, and the output goes to that. So this value is the error. This entire height here is the steady state error. If we had a ramp, then the output, what would happen? If you put a ramp here, the output will also be a ramp. If you put a ramp, the output is also a ramp, and then the result here would be something like that. And this tends to infinity as time tends to infinity. Right? Because the input here keeps increasing over time, the output keeps following that, and this is now deviating from 0, and that deviation increases as time tends to infinity, and therefore in steady state, as time tends to infinity, this actually doesn't reach steady state because, well, in a ramp steady state, but as time tends to infinity, this output keeps increasing, and therefore the error tends to infinity. All right? But if we did only a ramp, then we have a finite, only a step, we have a finite value. If you have a ramp, then it goes to infinity.
Excuse me, Professor. So if the error became infinity, this is favorable or unfavorable?
Sorry, I didn't understand the last part. If this is?
This is expected or not expected?
Yeah, it is. It's perfectly expected, right? Because if you put a ramp here, you shall see a ramp there. The problem is that anything that deviates from 0 is an error now, because we want the system to be 0. See, we cannot make the output 0, but we can make the desired output 0. Even and yet the output is following the disturbance. So anything that deviates from 0 is now the error. So this makes perfect sense. And that once again, this is a very important message here. If you want the output to go to 0, we cannot set y to 0. That's the system's output that we have no control over. We only have control over the input. So the best we can do is to set the input to 0 and make sure that the effects of the disturbance don't deviate from 0 too much. Don't make it deviate from 0 too much.